The point is that our observations and theories are accurate. The fact is that heavier stable elements with higher atomic numbers, which have more protons, neutrons, and electrons than any Earth elements, do exist. However, up until this point in history, there has been no physical evidence to prove this. But now that proof is here. The most important attribute of these heavier stable elements is that the gravity A wave is so abundant that it actually extends past the perimeter of the atom. These heavier stable elements literally have their own gravity A field around them, in addition to the gravity B field that is native to all elements. No naturally occurring atoms on Earth have enough protons and neutrons for the cumulative gravity A wave to extend past the perimeter of the atom so you can access it. Even though the distance that the gravity A wave extends is infinitesimal, it is accessible, and it has amplitude, wavelength, and frequency just like any other wave in the electromagnetic spectrum. Once you can access the gravity A wave, you can amplify it just like we amplify any other electromagnetic wave. To demonstrate how a wave is amplified, we can use this oscilloscope, and as you can see, it graphically depicts the tone you hear as a wave. As we amplify the tone, you can see that the size or the amplitude of the wave increases, giving us a more powerful version of the same identical wave, and thus the tone sounds louder. In like manner, the gravity A wave is amplified and then focused on the desired destination to cause the space-time distortion required for space travel. This amplified gravity A wave is so powerful that the only naturally occurring source of gravity that could cause space-time to distort this much would be a black hole. This brings us back to our original question: how do you generate a gravitational field? You must have access to an element which is heavy enough for the gravity A wave to extend past the perimeter of the atom. Then you can access and amplify it for space-time distortion. To complete our 3 science lessons, the last question is, what is the power source for this type of travel? Well, for those of you with limited knowledge about power sources, I'm sure you can probably imagine the enormous amount of power required to cause a space-time distortion for this type of travel. After all, we're amplifying a wave that barely extends past the perimeter of an atom until it's large enough to distort vast amounts of space-time. For those of you with extensive knowledge about power sources, I'm sure it's probably even more puzzling as to how it's possible to have a compact, lightweight, onboard power source that can provide this much power. For everyone to understand that, I need to further explain a couple of things we briefly touched upon in the last question. If you remember, I said that for the most part, we synthesize or create heavier elements in accelerators, and their stability decreases as their atomic number increases. So what does this all mean? Well, we synthesize these heavier, unstable elements by using more stable elements as targets in a particle accelerator. We then bombard the target element with various atomic and subatomic particles. At this point, transmutation occurs, making the target element a different, heavier element. This element now has a higher atomic number, as the atomic number simply indicates the number of protons in the nucleus of the atom. So this is what I mean when I say their atomic number increases. What does their stability decreases mean? The length of time which an element exists before it decays determines its stability. Atoms of some elements decay faster than atoms of other elements, so the faster an element decays, the more unstable that element is considered to be. When an atom decays, it releases or radiates subatomic particles and energy, which is the radiation that a Geiger counter detects. As you can see, this Geiger counter is detecting the radiation from this uranium, which literally means that the Geiger counter is sensing the subatomic particles which are being released or radiated as the uranium decays. Those elements in which nuclear radiation can be consistently detected are radioactive elements. These heavy elements, which we synthesize in particle accelerators, are of the radioactive variety, and they decay very rapidly. Since we're only able to make a few atoms of these elements, and because they decay so rapidly, we're not able to observe much about them. This is what I mean when I say their stability decreases. However, there are elements with higher atomic numbers which are stable, even though they don't occur naturally on Earth, and we can synthesize them in particle accelerators. These are the elements in the 114, 115 range which don't appear on a periodic chart. Beyond element 115, the elements become unstable again, And in fact, element 116 decays in fractions of a second. This finally brings us to the power source. The power source is a reactor which uses this element 115 as its fuel. In this reactor, element 115 is used as a target and is bombarded with protons in a small particle accelerator. When a proton plugs into the nucleus of an atom of 115, it increases its atomic number and becomes an atom of element 116, which, remember, decays instantly. What element 116 releases as it decays, or what it radiates, is antimatter. What is antimatter? Antimatter is the exact counterpart of matter, which has a charge and a spin that is in the opposite of all matter. When combined with any matter in our universe, antimatter reacts and completely converts to energy. And remember, the rapid conversion of matter to energy is what we generally call an explosion. To demonstrate the explosive power of antimatter, let's pick a random area where an atomic bomb might explode. Oh, let's say Iraq. And for demonstration purposes, let's say an atomic bomb would explode, for instance, in, Baghdad.